Welcome to the Crazy Hat Chemist. So here we go, another video on kinetics. So hopefully we have a nice fast rate law with this one so that we can get this one moving along. So here we go. 1, 2, 3, BAM! All right, we're going to derive the rate law and the rate constant for this problem number 1. So we're going to derive the rate law and the rate constant, which is K. So we have this decomposition reaction. The decomposition is CH3CHO, and that is acid aldehyde. And it's going to decompose to methane, that's CH4, and carbon monoxide, that's CO. Okay. All right, so we're given a set of data that we're going to have, and this is the disappearance of the acid aldehyde on this problem. You notice that we have reactions or experiments 1, 2, 3, and 4. I've highlighted them, alternating colors of white and yellow, so you can see horizontally where they're lined up. The second column is the initial concentration of the acid aldehyde, and that's in moles per liter. Then the third column is the disappearance of the acid aldehyde, that is in moles per liter seconds. Okay, so what we're going to do is we're going to analyze these experiments and this data to derive the rate law and then also the rate constant. Okay, here we go. Let's see what we can come up with. We're going to take a look at experiments 1 and 2, and I've chosen experiment 1 and 2 for a particular reason, so let's find out why that is. So I've taken a look at experiment 1 and 2 because if you look at experiment 1 and 2 and you look at the concentration of the acid aldehyde, it goes from a 0.10 molar to a 0.20 molar. So it's doubling in concentration from experiment 1 to experiment 2. Now, in experiment 1 to experiment 2, we're going to look at the rate of this disappearance because it is a decomposition reaction, and we're going to look at this disappearance. The disappearance of the acid aldehyde is going from 0.020 in experiment 1 to 0.081 in experiment number 2, and that's a quadrupling or a 4 times factor. So if you double the concentration and you quadruple the rate, then that is a second order rate law. We're really trying to figure out, is it 0, first, or second order? And if the concentration does not, if the rate does not change with a change in concentration, it is 0 order. If the concentration doubles and the rate doubles, that is first order. If the concentration doubles and the rate quadruples, that is second order, as in the case here with experiments 1 and 2. And so this leads us to that second order for the disappearance of the acid aldehyde. Now, I'm going to take a look at another set of experiments here just to validate the fact that this is second order, and I'm going to take a look at experiment number 2 and 4. Okay, with 2 and 4, I'm again choosing experiments 2 and 4 for a particular reason. The numbers are easy, they're easy to see. So between experiments 2 and 4, the acid aldehyde concentration initially is 0.20 with experiment 2, and at experiment number 4, it's 0.40. That's a doubling in concentration. Now I'm going to look at those two experiments, but with the disappearance of the acid aldehyde. And if I look at the disappearance of the acid aldehyde, I have 0.081 all the way up to 0.318, and that's a quadrupling, or times 4. So again, if I double the concentration and I quadruple the rate, that's second order, and that's why I get second order here again. Again, if you change the concentration in any way and the rate does not change, that's 0 order. If you double the concentration and you double the rate, that's first order. If you double the concentration and you quadruple the rate, that's second order, as in the case right here. So now what we can do is write the rate law. So here is the rate law for this reaction. Rate law is equal to the R is equal to the rate constant, that's K, times the concentration of the reactants and to the power of the order of that particular reactant. And you need to remember that all rate laws are relative to reactants only, never to products. So that's really important. There's only one reactant, so that makes this really easy. And we just derive the order of that reactant by comparing experiments 1 and 2 and 2 and 4, and that's how we derive that stoichiometric coefficient, if you will, on that, or that, excuse me, not stoichiometric coefficient, that power, which is 2. All right, so now that we've derived the rate law, we need to now derive the rate constant and the units associated with that. Now, what we can do is we can pick any of the experiments 1, 2, 3, or 4. I'm going to choose experiment 3. Why experiment 3? I didn't use it in deriving the rate law, but it actually really doesn't matter. You can use any of the experiments you want, and this would be a good assignment for you to check. Once you have this rate law, is derive the rate constant and the units for the rate constant for using experiment 3, and then try another experiment, either experiment 1, 2, or 4. So here we go. What I've done is I've taken the data from experiment number 3, that is the rate at 0.182 moles per liter seconds, that's equal to the rate constant, K, times the initial concentration of the acid aldehyde that is at experiment number 3, that's 0.30 moles per liter, and that is to the power of 2. And so now what we're going to do is derive the value and the units for that rate constant. And mathematically, I'm going to solve this. I get the rate constant at 2.0, that's the numeric value, and then the units are liters per mole seconds. Those are the units. So now I have the rate constant. So just so that you know, the rate constant, K, can be used with any other concentration, even concentrations which are not involved in these experiments, which I have on this slide. And that is assuming one assumption, and that is assuming that this is happening at the same temperature, because the rate constant is temperature dependent. All right, hopefully you got that for this rate reaction number 1. Now, before you go away, I do have this same reaction of which I'm going to show you in an alternate method. So this is one method in which you can use, and I'm going to show you an alternate method of using that and solving for the rate law and the constant and the units in the same problem. So now you have a set of tools to hammer this problem out. I'm going to give you another set of tools. You have to choose which set of tools is going to work out best for you. So here we go. Let's give the alternate method a try. So we're still deriving the same information from the same set of data, and we're deriving the rate law and the rate constant. Okay, we have the decomposition of acid aldehyde to methane and carbon monoxide. And just as a quick little reminder, the rate law is always dealing with reactants only. Okay, and so we have the same set of data that we had before. And so what we're going to do is we're going to pick 2 experiments here. We do know that the rate law is rate is equal to a constant times the initial concentration to the power of. So that power is going to be more than likely a 0, a 1, or a 2. And remember, if you look at some of the previous slides that I've had, previous videos on this unit, those values, those exponents for the order of those reactants can be negative numbers, they can be fractions, they can be a whole variety. But the vast majority of them are either going to be a 0, 1, or a 2 for practical purposes for working out problems. Okay? So the rate law, rate is equal to a constant times the initial concentration to a power. So what we're going to use is use that information here and compare 2 different reactions. I'm going to compare reactions 3 and reactions 2, something that I didn't do on the previous one. And you know that I have, what I just showed you right here, is that I have both of those basic rate laws set up. Rate 3 in the numerator over rate 2 in the denominator is equal to the rate constant in the numerator and denominator, because that doesn't change, times the initial concentration of the acid aldehyde. For on the numerator, it is for reaction 3. On the denominator is for reaction number 2 by the lower subscript numbers that you see there. And what we are going to solve for is x, and that might be really hard to see right there, but I'm going to highlight what we are solving for, and that is the order of the acid aldehyde here, and that is for x. So what we're going to do is we're going to plug in the information, that is the data from reactions 3 and 2, and then we're going to solve for x. That x is going to be the order of the reactant of acetaldehyde. So I'm plugging in the data for reaction 3 and 2. In the numerator is for reaction 3. That is, the rate is 0.182 and the concentration is 0.30. And for reaction 2, in the denominator section of this fraction, I have the rate as 0.081 times is equal to times a constant, the rate constant, and 0.20. Again, I'm solving for x. So when I solve for these numbers, do a little division here. I have 2.25, that is the quotient of the 0.182 divided by 0.081, that's the 2.25, is equal to 0.3 divided by 0.2, that's equal to 1.5. And that's to the power of x. So I'm going to solve for that power of x. That power of x is equal to 2. This is the order of the acetaldehyde. You should note that this is the same value that you received in the previous non-alternate method. So now what we're going to do is write the rate law based on this information. So the rate law is equal to R equals K, the concentration of the acetaldehyde, to the power of 2, because that is the order of the acetaldehyde. That is an alternate method. Now what we need to do is, we've derived the rate law, we need to derive now the rate constant value and also the units associated with that value. So let's see what we come up with that. So I'm going to derive the rate value and the constant here for using experiment number 1. And now again, remember, we can use experiment 1, 2, 3, or 4. It really doesn't matter. It's entirely up to you. I've chosen experiment number 1. No particular reason. It really doesn't matter. But we're going to derive the value of k without the units. Some students find that this is easier if you get the value of k independent of units and then the units independent of the value. And then what we're going to do is combine those two things together, and then we're going to get the rate constant and units and shove them all together. In more complicated problems, this is probably the easier process for students to do. So I'm just going to put in the numbers, and that is 0.020 for the rate using experiment 1 is equal to k times the concentration, the initial concentration at 0.10, and that's squared. So I'm going to solve for k mathematically. I'm going to take that 0.1, I'm going to square it, I'm going to divide that number on both sides, and I'm going to solve for k, and that value is 2.0. Again, you should recognize that on the previous slide of this same problem, we solved for the value of k at 2.0. This is no different. We're getting the same data. We're getting the same value of k. Excuse me. Now what we're going to do is derive the units of k without the numeric value of k. We're going to still stay with the same experiment number 1. Okay, and so what I've done is just plugged in the units here at for the rate is moles per liter second is equal to k, and the initial concentration of the acetaldehyde is moles per liter, and of course this is second order, so that's going to be squared. So I'm going to rearrange this, put k on one side, put all the units on the other side. I'm going to cancel out some of these. I'm going to cancel out the moles in the numerator, the squared term in the denominator for moles, the liters in the denominator, and the squared term for the liters in the numerator. And then what is going to remain are the units for k. So the units for k are liters per mole second. So now that I have the value of k and the units for k solved independently, I'm going to put them together to get the value of k and the units for k. And I'm going to combine the units and the value of k together, and here's what I got. 2.0 is the value and liters per mole second. So now I have the value of k. Remember, k is dependent on temperature. So whatever temperature this reaction happened at, you can use that value of k and the rate law to determine any rate or concentration given either concentration or rate. I'm hoping that problem worked out well for you. I'm giving you two different methods of solving that problem. I am the crazy hat chemist, and of course I've got myself a crazy hat. This is root beer, and thank you very much for two of my former students, Wyatt and Jordan for giving me this hat. I greatly appreciate it. Give me a thumbs up if you like that video. Hopefully you learned some cool chemistry. Look at some of my other videos. Please subscribe to my YouTube channel and pass it all along. I greatly appreciate that. I hope you have a great afternoon, great morning, great evening, whatever it is, wherever you are. Have a great day. Bye now.